Okay, so this time around, we want to continue our discussion on internal forces, but this time we want to look at how we treat distributed loads. So for distributed loads, you notice that unlike the previous question or the previous example, where the loads which were present were at specific points, now we look at cases where instead of being applied at one point, the load is presented as a distribution, meaning it's acting not just at one point, but it's acting through some section of the load. So how do we handle such cases? So this is what we're going to discuss. So basically, there are different ways in which these loadings will be presented to you. So it might be that you have a member like this, and then the distributed load here is maybe something which is uniform. So this is basically just a uniform distribution where the force throughout this structure, it can be throughout or maybe through the first part of the structure and so on, is uniform. So here, this will be presented something like this to just show you that this distribution starts from somewhere here and it stretches throughout this structure in the same way. So here, the distribution can be given maybe by some expression. So they'll say, in this case, to actually understand how much this force is going to be, or the load, what the load is going to be, they will say maybe this is 10 kilonewtons per meter. What this is telling you is that the amount of force present depends on the length of the beam you're dealing with. Meaning, for every meter of the beam or every meter of the member, the force equivalent there is going to be 10 kilonewtons. If you have 2 meters, the force there is going to be 20 kilonewtons. So basically, that is that. For this one to determine how much the force is going to be, you multiply the length of the member multiplied by the distribution which has been given to you. Another possibility is that instead of giving it to you as a uniform distribution like that, it can be that the distribution is more like changing, but the change can be linear. So it can be that maybe they'll present it something like this. And then now you have the force is greater this side, but it's less as you keep on going through that length. So as the length increases, the load on the beam, on the member, keeps reducing. So this is another common presentation that you encounter. It's possible to find ones where you have a curve as the one controlling the distribution, but they are rare. I think for this concept, usually they'll use this. But once you've understood centroids and how to handle them, everything is possible. So in an event that you have something like this, just look at it as if it is part of a bigger picture. If it were linear, a linear distribution, meaning that it would have been complete to have this extra piece as well. Meaning to understand the load due to just this section, given that the length here of the structure maybe is L. So let's say they've given you the distribution, the load here to be same thing, 10 kilonewtons per meter. In this case, you do not just multiply 10 kilonewtons. You don't just multiply this by the length of the distribution, because if had it been linear, this upper part would have been present as well. But because it's not there, it's like we have half of what it would have been if it were a uniform distribution. In other words, this will multiply by half. See that this is basically just the area of a triangle. In other words, when the distribution was linear like that, uniform like that, we end up by just multiplying whatever this is, multiplied by the length, which is, you can just look at it as the height times the breadth or the length of the beam. But for something like this, because this seems to be something triangular, we can easily just use the area of a triangle. Half the height will be the distribution there, which is 10 multiplying the length of the beam. So basically, this is what we're looking at. A good example is this one here. How do we handle that? Because earlier I was just describing what the distribution is and how to find the whole force from the distribution. There's also going to be a concept of where that force is acting. Let's use this question for target practice. So the idea would be similar to what we did earlier on. The first thing you want to do is determine a free body diagram of your structure. So get this member. If necessary, we'll dismember it. In this case, of course, we'll just remove the support there. So due to the support, what shows up when the support is removed? I think we can remove this now that we've discussed through. Okay. All right. So at point A, where we have just, we so to say at point A, we had a fixed support there. So once we remove this when drawing a free body diagram, due to the fixed support, we're going to have reaction. So we can assume the reaction here is going to be going to the left, A in the X. We can assume the vertical reaction because all I'm saying is everything else is going down. So we can assume the vertical reaction is going to go up. Again, you can assume anything here, it's still okay. Then lastly, being a fixed support, we expect a rotational reaction. So for the rotational reaction, again, we can assume something like this. A moment at A. Other than this, what do we have? When you look at the question, they haven't said anything about the mass. In some cases, it is possible that they'll give you the mass of the member. If you're given the mass of the member, then of course you're going to take it as a weight. It will also be acting as a force. But here, of course, nothing has been mentioned there, so we're going to take it exactly as it is, as if it's just a beam. We'll just look at the distribution there on top. So from the distribution on top, we have it's given as 1200 Newton per meter. So we now want to present this as if it is just one force acting at one point. So this is where we're trying to say, okay, this distribution, if we were to combine it or just look at it as if it was just one force acting at one point, what would that force be? Seeing that the distribution here is triangular, for a triangle, area of a triangle, half, the height will be the distribution at its highest point, which is that by the length of the beam. The full length of the beam, we have 1.5 plus 1.5. That is basically going to be a 3 there. Okay, so this is going to be a 3 meters for the whole length. So if we're going this way, half of 12, that's going to be 600. 600 by 3, this is going to be 1800. Okay, so I hope that's okay. Half of that, then that's going to be 1800. It's going to be in newtons. So here you can present this as 1800 newtons. Now, where will it be acting? So in this case, this 1800 newtons, where will it be acting? So this is what I was saying, that you need a little bit of CEE here. Because for something that is triangular like this, you see, the center, this force will be acting at its centroid. And the centroid for something triangular, we have to know that it's a third from either edge, meaning it has to be a third from here, a third of the full horizontal length. If the full length is 3 meters, it has to be a third of that 3 meters. So basically, we see that it will have to be at a meter. All in all, this is going to end up acting somewhere here, a meter from point A. That is where that 1800 Newton can be presented. Here I was just trying to draw a free body diagram for the whole structure. But let's understand the whole question and see how we're going to work it out. But being able to draw a free body diagram is the first step. So in this case, they want us to find the normal force, the shear force, and the bending moment at point C. Where is point C? Point C is here. By looking at the distances they have given us, point C is right at the middle of the member ABC. So it's right on the middle. So if you look at the presented diagram this side, if it is right on the middle, what does it mean? It means that even the heights will be halved. So this height here, if at its topmost point, this is 1200 newtons, then it implies that even here, it will have to be half of that using proportions. So it means that if this is 1200 newtons, half of 1200, here, the distribution will have to be at 600 newtons per meter. So just by looking at this piece here, this has to be 600 newtons per meter, as if we just decide to go with that part. Now we want to just get this piece so that we don't have to start trying to understand what is happening at that particular point. We can include them as well, but we want to avoid working with them if it is possible. So if we went to just point C there, how would it look like? So here we'll draw our free body diagram just up to point C. So it's like now we are cutting our section already at point C. We're going to break it up right at that point. So if we are to break it up right at that point, what happens? So get this point or this piece, we notice that to the right of point C, notice that there are no any other forces present already there. There are no any other forces except the distribution itself, because the distribution there continues. So the distribution here would continue until when it reaches point B there. So let's include it for now. So for now, the distribution here, we've included it as a distribution because even though we combined it here to see what it would be when it's acting at one point, it depends on the section we want to get. If we were to get the section to the left, of course, this 18 is for the whole thing when it is together. So this 18 is for the whole thing when it is together. If you wanted to get AX, AY in the moment about A, this is the free body diagram you'll be analyzing. But we want to pick a section that doesn't need us to know this. So if you can still find them, of course we can, but strategically, we're going to pick a section that doesn't need us to find that. And by doing that, since we're getting our section at point A, we're going to pick the section to the right. We're going to pick the section to the right of point C. I think I said A earlier. We're going to pick a section to the right of point C. And the section to the right of point C does not involve this. It only has this part. In this section, what will be the forces there once they're exposed? We know to say here, we're going to show that the shear force will be going upwards. V at C, the normal force will be going to the left. Normal at C, and finally, the bending moment will be going this way. Next, the distribution. Like I pointed out, seeing that this is exactly halfway of the full triangle there, if the triangle at its maximum height here was measuring at 1200, it would mean that halfway point here, at its highest point, it must read half of that 1200, which is 600. So since we are breaking it up to halfway here, this distribution, just this part here, this must have a highest point of 600 newtons per meter. The rest of it must be governed by that. So just for the section on the right here, we can actually combine this distribution. Again, since that distribution is rectangular, it's triangular still, we're going to go with half, and then we'll go with the 600 by the distance now. The full length for this piece we have selected, it's half of the full one. The full one was 3 meters. This section we've selected, it's half of that 3, which is 1.5 as indicated here. So multiply by 1.5. So if we do the math here, half of 600 is a 300. And then we'll multiply the 300 by 1.5. So here we're getting a 450 as a combined combination, the overall effect of that distribution. So instead of presenting it as a distribution now, we're going to present it as just one force acting at one point. So that distribution will act as if it's just one force acting at one point. Now, as I pointed out, this force will act through the centroid. So we've seen that it will be 450 newtons. It will act through the centroid of a triangle of that nature. So a triangle with a base length here of 1.5. Where will be its centroid? So from centroids, we know to say that the centroid will have to be a third from here. So let's find a third of 1.5. So we have 1 over 3 by 1.5. So this will give us 0.5. So we're now seeing that here, this will actually act 0.5 meters from that face. So this is what we're going to have there. Now let's present that piece without the distribution. So we're going to make it slightly longer. We have this. The forces. We have the shear force. We have the normal force. Then we have the bending moment. And 0.5 meters from C, we have a combined effort of that distributed load, that 450 Newton load. So this is what we have. So from here, we can now analyze what is happening. When we sum forces in the x-axis and equate to 0, we see that straight away by doing this, we have, so here we end up having NC being equals to 0. It's the only one in the x-axis. By summing forces in the y-axis and equating to 0, we have VC, the shear force, going up, positive, minus the 450 going down, negative, equals to 0. So this implies that VC, the shear force, will also be equals to 450 Newton. Next, we'll take moments about point C. So about point C, it implies that VC, no rotation, and C, no rotation. So the moment there, which is the bending moment, will cause a rotation. It's going to be clockwise. So that is going to be negative. Next, we have the 450 there. The 450 as well is causing a clockwise rotation. So it is also going to be negative. But what will be the distance? Remember, it's the distance from point C. And we saw that that distance was 0.5 meters. So it will be 450 multiplying 0.5. Those are the only forces causing rotation. So this has to be equals to 0. From here, we have MC goes to the right, becomes positive. We now have MC is equals to half of 450 with a negative. Should be 2 point, not 2 point. It should be 225 Newton meter. So that becomes the moment, the bending moment about point C. So for our second example, we have this one. Now when you look at this one, notice that we have a uniform distribution that is given this side, but we just have a little bit of more information here, a little bit of more parts for our structure. They're saying determine the shear force, determine the normal force, shear force, bending moment acting at point B of the two-member frame shown. Okay, so this is what we have. Where is point B? Point B is here. So how do we understand that? The first thing we need is a free body diagram. So Notice that we have two pieces here. This is a frame and it has multiple parts. So we have to first dismember those pieces. So first we have the member ABC. So for the member ABC, we have a pin at point A. So from that pin, we're going to have reactions in the horizontal and in the vertical. So you can assume to the left, AX. We can assume up here, AY. Next, nothing else is there apart from that distribution. So this being a linear distribution, it can also, that's basically something rectangular. It's like you have a rectangle. And here, all you have to do is multiply the distribution that has been given there, which is 50 pounds in this case, multiply it by the length of the structure. Once you've done that, you would have found the concentrated effort of that distribution. And then that is going to be applied through its centroid. For a rectangle, the centroid is exactly halfway of the base length. So that is where it's going to be. So in this case, halfway, basically since this is for here and for here, halfway means that that distribution is going to act through point B if we put it all together. And since this is 50 for every feet, so to get the combined effort, it'll be 50 per feet multiplying the full length, which is 8 feet. This will go with that. 5 by 8 is 40. So for the whole thing, we get 800. So right through point B, we're actually going to be experiencing a 400-pound load. Lastly, we have point C here. Since we are dismembering the whole structure here, if we look at this member CD, this is a two-force member. So this member only has two forces, and all these forces are at its ends. So for a two-force member, when we remove it, all the forces are going to be presented such that they are along the axis of the member. So even though we are seeing that it is pinned either end, being a two-force member, the best way to represent is to use forces along its axis. So we can assume the forces are such that they are compressing it, FDC, meaning even this one must respond the same way. And for a two-force member, if this is FDC, even this one down here must have the same label because they're going to be the same. Remember, nothing is happening inside, meaning the force inside is going to be the same. The normal force along this member is going to be the same throughout. So if the force is FDC, it will be the same throughout, like that. Funny thing is, the same force is what it is going to exert at the point C there. So if I labeled FDC to be pushing my member this way, it implies that to C, it will actually be pushing on to C, like that. So that should you, when you put these back together, they should oppose each other so that they give us 0 at that joint. So you bring them back, they should oppose each other so that you get a 0 at that joint, since of course it is an equilibrium. So basically, this is what we have here. This will have the same label FDC. Okay, now having done that, now we want to see how we approach that section of ours to find what is happening at the point B. So for the point B, we're going to now break this member, section it right through B. What are we going to have? So I'll draw both sides here. So draw both sides so that we understand what is happening there. First, let's draw the side with the point with AX there. So for the side with AX, what do we have? For the side with AX, you have this. AX was labeled to go this way. AY, we chose AY to go up. And then, of course, once we dismember, once we break it at that point, at point B, we expect that we're going to have a shear force. We expect that we're going to have a normal force and of course we expect a bending moment. The other one, however, of course we still have the distribution, because the distribution is also present on top here, but this time around we'll present it as just a concentrated load at one point, and since again it is a uniform distribution, we just multiply the 50 for just this half from A up to B. The length is 4 feet, so it will be 50 by 4, which gives us 200 pounds there. And this being a uniform distribution, to be acting through the central point of that 4 feet, which will be 2 feet from either side. So it will be 2 feet from A to there. It will also be 2 feet from B to where this point will be. In the same way, when we draw the other half, for the other half, we see that firstly, of course, we have the internal forces which will now show up. The shear force will now have to point up. The normal force now point to the left. And then the bending moment will now have to go clockwise. And then, of course, you also have the distribution here. The distribution, of course, here, this is still linear, so this will also be at its centroid, halfway point. Also, 2 feet from either end. And of course, when you follow the same technique, this will still be 200 feet even for this one. But this will have an additional one. It will also have this piece, FDC. So for this case, you quickly observe that regardless of the section you want to work with here, there will be an extra unknown. For example, in the previous example, we avoided working with the support reactions and selected the other side, seeing that it didn't have the support reactions. That allowed us to solve the problem without having to know the support, what is happening at the support. But for this one, we have this extra force at the far end, implying that we would either have to first figure out what this one is and then use this piece. If we can find FDC, then this will be enough to help us understand what is happening at B, or figure out what is happening at that support. If we can understand what is happening at the support, then we can also maybe be able to use this piece as well. So the first thing is, maybe let's not go straight to the sections. Let's first understand what is happening to the support. And the best way to understand what is happening to the support is right before you even section it to get the internal forces. So before you expose your internal forces, let's understand what is happening to the structure. So this is why the first free body diagram is important. So when you analyze, sometimes you can quickly see that you won't need the support forces and quickly go ahead. But in some cases, as you've seen for this one, it's important for us to know, to analyze the circuit, the circuit, to analyze the structure before we show the internal forces. So let's analyze it. Since the whole structure is in equilibrium, any piece of it we pick must also be in equilibrium. So based on that, let's see what we can do here. Let's try to figure out what these are. So first thing that we'll do is this force FDC. Let's present it in component form so that we can show it off as a vertical force and a horizontal force. So is it possible for us to do that? Well, yes. You see, that force is acting along this line, meaning we can easily say it is part of a triangle, with the vertical here being a 6 and this here being an 8, 4 plus 4. So for this, with a 6 here and an 8 this side, we quickly see that we can actually figure out what is happening here. So how do we work it out? We can even come to just get the angle that is here. So that's the angle that we use to resolve that force there. So I can use tan. If I say this is theta, I can say theta will be equals to tan inverse. The opposite to this will be 6. The adjacent will be 8. So this will allow me to get the angle there. Okay, so I have 36.87. So with the angle figured out, 36.87, we can now bring it here and say that this force will be acting such that the angle here is that theta. So we can now use that to get the vertical component and the horizontal component. The vertical component will basically be here. It will be opposite to that theta. So we can easily say that it will be given by whatever this is. This is we say DC, FDC, and then sine 36.87. Okay. So once you have obtained that, this of course will be FDC, then cos 36.87. So 36.87, whatever the angle here is going to be, that's what you're going to be using there. So once you have those, let's bring them here. So we're saying that present this force FDC in component form. And we've seen that the horizontal component will be FDC cos 36.87. The vertical component will be FDC sine 36.87. So with this now done, you can take moments about A. So let's take moments about point A and equate to 0. So at A, this allows us to eliminate these at first and help us find what FDC is. So once we eliminate those at A, what do we have? About A, the 400 is causing clockwise. So I have minus 400. So the distance from A to where the 400 is, remember that is halfway of the 8. So that will be by 4. Then plus the FDC sign will be causing anti-clockwise. So to be positive. So FDC sine 36.87. This will multiply the full length from A up to where C is. So that will be 8. FDC cos passes through A. So because it passes through A, it will not cause a moment about A. So we'll only have these two equals to 0. So in the end, this goes to the right. FDC will have to be equals to the 400 by the 4 over the 8 multiplying sine 36.87. I've just made this the subject of the formula. So here we get 333.3 pounds. So once we have FDC, notice that we can now go on and say, okay, let's sum forces in the x-axis. Let's see what we're going to get there. So in the x-axis, of course, equilibrium equals to 0. We have two forces, AX to the left, and then FDC cos to the right, positive. So we're going to have FDC cos 36.87 positive minus AX negative is equals to 0. And when you work out this, you should be able to obtain AX as, so of course, since we already have FDC as this, substituted, AX comes out as 266.7 pounds. In the same way, we can sum forces in the y-axis equal to 0. In the y-axis, we have three forces, AY, 400, and FDC. AY goes up, FDC goes up, so it will be positive as well, 333.3 sine 36.87, but the 400 goes down, goes to 0. In the end, when you solve this, AY comes out as approximately 200 pounds. After you have obtained this, notice that you actually now have all the pieces of the puzzle. At this point, it's up to you which one that you want to use, because already we found FDC as well, meaning you can easily use this piece to find what these three are going to be. But we also found AX and AY, meaning you can still use this piece to find what these three are going to be. So any piece here is going to work. So we'll go with this one. So when we use this one, sum forces in the x-axis equate to 0. We see that NB to the right positive, AX to the left negative equals to 0. Here for once we see that NB will not be 0, or there are other examples it was 0. AX 266.7, NB is equals to AX 266.7. The normal has been found. Some forces in the y-axis equate to 0. AY goes up, 200 goes down, negative. VB goes down, is equals to 0. AY was found earlier on. AY came out as, we found it somewhere way up, 200. So you have 200 here, minus 200 here again, minus VB is equals to 0. Guess what? VB has come out as a 0. So the only thing left, it's the moment. For the moment, we'll take the moment about the same point where these are showing up. So we'll take the moment about that, eliminating this and this. But guess what? Even AX comes to pass through that point. So here, even AX will not cause a moment about that point. So if we take moments about the point B, we now have the moment, the bending moment itself, MB, anti-clockwise, the 200 also causing anti-clockwise. So this will be plus 200. The distance to the 200, remember, the whole from A to B, it was 4. And the 200 was at the centroid, which is halfway off the 4, meaning this has to be 2 here. So this is going to be 200 multiplying 2 feet. Finally, AY at the far end here. AY will be causing clockwise, so it will be negative. AY, if you recall, AY, we found AY as 200. So I have 200 as AY. The distance to AY will be the full length from A to B, which is 4, equals to 0. Then from here, we simplify this for the bending moment. So here, the bending moment will be equals to, this goes to the right to be 400, becomes negative. This goes to the right, becomes positive 4 by 2, that will be 800. So when we solve this, we have 400. But here we're using the pound and the feet, So this would be in this form as the bending moment.